At the beginning, we don't have energy. At the end, we have energy. Plus the change, oh, by the way, there is another force here acting. The work net. So it's the work done by P plus the work. If we go by this, let me just, I prefer to use the second. I could use the first. If I know that the work done by the spring, which is opposite to the change in potential energy, opposite to the change in potential energy will be negative K over 2 x final squared minus x initial squared. You could do this, or you can say the work done by the non-conservative force, and using the second, I could use the first, is equal to delta E, which is delta K plus delta U, is the same. So the work done by the non-conservative force is just Px, which is 1/2 mv squared, that's the change in kinetic energy, plus the change in potential energy. What is the change in potential energy of the spring? At the end, when it's passing through the equilibrium position, what is the potential energy? 1/2 kx squared. But when it's at the equilibrium position, what will be? Zero. At the equilibrium position. At the equilibrium position, there is no potential energy. At the initial position is when it's maximum extended. How is called that? Or when it's so I mean, it was not the amplitude, because we didn't say that they said what is the speed of the block when it's 13 centimeters. We don't know if that will be the maximum point. Okay, but anyway, it's x. K over 2 x squared. This, do you have P? Do you have x? 1/2 mv squared and this. So basically this will be the equation to find P. Px plus K over 2 x squared. This is what I said, that is this. The work done by P plus the work done by the spring, both. Remember, the work done by the spring is K over 2 negative, K over 2 x final, but x final is 13, and this is 0, so this will be negative. So if this is this, we have 0 is the, no, my bad. It starts at the K over 2 x squared minus 0. The final is K over 2 x squared minus 0, because started at the point of equilibrium. So if you move this to this side, will be negative, which is what I said. This is the work net, and that will be equal to 1/2 mv squared. This is using the first theorem. This is using the second theorem. You can see that they are equivalent. First and second theorem. But anyway, so what you need to find is V. Let's say that you have the same problem, but let's assume that you applied that force, that P is given. Let's assume that you have the same problem now, but you released from 13 centimeters the object. From 13 centimeters the object. Typical question. So let's say these are additional questions in question 1. In question 1, this is the solution. So you can solve for B and that's it. You have everything. Let me just change slightly that problem, and I will say, we have the same problem, but no force. You just extend to 13 centimeters. X is 13 centimeters, and you released on a frictionless surface, right? The question can be, so the same question 1, but reformed. A, find the amplitude. So you extend 13 centimeters and you release. Find the amplitude. B, if the mass of the block, which is not given, yes, it's given, 10 kilograms. So find what will be omega, T, and F. C. Find what will be the velocity maximum which happens at the point of equilibrium. Find the velocity maximum which happens at the point of equilibrium. D. Find what will be the velocity passing through 7.5 centimeter. These are different questions I can ask from energy perspective. So, assuming that there is no force, you just extend the 13 centimeter and release. What will be the amplitude? 13 centimeter. So the amplitude is 13 centimeter, the maximum distance from the point of equilibrium. Nothing to calculate. So this is a 13 centimeter. How can I find omega? The square root of K over M. Do you have K? The spring constant is given. That value that is given in Newton per meter. 0.80, whatever. Is kilo? Kilonewton per meter or Newton per meter? Kilonewton per meter. So you multiply by 1,000. Okay, do you have K? Yes. Do you have the mass? Yes. Can you find the omega?
Yes.
Is this dependent on the amplitude? No. For this reason, this motion is called simple. Good. The frequency, can you find the frequency? 1 over 2 pi the square root of K over M. Remember that this formula comes from omega is 2 pi over T, or 2 pi F. Omega is 2 pi F, or 2 pi over the period. Good. Can you find the period? Yes. 2 pi the square root of M over K. Good. If I double the mass, the period will be longer or shorter? Longer. By how much?
4 times.
If I double the